Water is flowing over a copper plate via forced external convection, and we are to determine how much insulation is needed to be added to the plate to decrease the total heat loss from the plate by 90%. The learning objectives are conduction, convection, resistance networks, Cartesian coordinate systems, and forced external convection. We know the temperature of the plate, the K of the plate, and the insulation, the velocity, and the plate length. And we have to find the insulation thickness, and we're going to assume that there's 1D heat transfer, steady state, that it's constant K and H, and the average temperature is 40 degrees Celsius. Using an average temperature of 40 degrees Celsius, we can find the water properties at table A9. And then calculating the Reynolds number, we can then find the Newsett number, which is then used to find the H for the flowing water of 5,283. Then we can set up a heat resistance network with no insulation that'll include conduction and convection, and find the total heat transfer, or the total resistance, which can then be used to find the total heat transfer by dividing delta T by R total. And then the Q for no insulation is determined to be negative 91,057. Then, with the knowledge that the Q with insulation should be 10% of the Q without insulation, thus reducing the total Q by 90%, we can find the heat resistance network with the insulation to have the two different types of heat conductivity through the conductive heat transfer through the copper and then the insulation, and the convective heat transfer. We can find an R total where the only unknown is L2. And then using that, using the Q that's determined and the R total equation, we can solve for L2, which is 0.277 millimeters. And the next problem we have is a spherical potato with a radius of 0.03 meters that is wrapped in foil of a known thickness, and we're supposed to find the temperature of the potato at the interface between the foil and the potato itself. The learning objectives are deriving the conduction equation, solving the conduction equation, spherical coordinate systems. We know the radius, we know the temperature at the foil surface, and we know the temperature at 0.01 meters, as well as the thickness. We also know the temperature of the potato at 0.03 meters, and we can assume steady state, 1D heat flow, no heat generation, and constant K and H. The properties for the potato can be found at table A7, and then we can derive the conduction equation and simplify it such that if we know there's constant K and H, that it's 1D heat flow, that there's no heat gen, and that it's steady state, we can derive the following form of the conduction equation. And using the two boundary conditions that are present, which is the known temperature at 0.01 meters, as well as the fact that the two conductivities of the materials should be equal at the interface, we can solve for the temperature temperature profile and solve for C1 and C2 using the known boundary conditions to obtain the following temperature profile, and then plug in the radius of interest, which is 0.03 meters, to find that the temperature of the interface should be 30.62 degrees Celsius.